Mir fehlt eine Seite. Es fehlt eine Seite. Da muss ich einmal kurz wo rein. Okay. Aha. Das habe ich gar nicht angepasst. Okay, gut. Okay, ready? Almost. Kind of. Sort of. Dann notiere ich mir das. Du sagst, wenn du bereit bist. Ja. Okay. Ist das hier nicht? Okay, good. So let's continue. And what we talk about next is a so-called generic attack on hash functions. If you look at various recommendations, standardizations, or similar things, you will notice that if you look at recommendations for key sizes for symmetric encryption schemes and for hash length, the length of the hashes for hash functions, there's usually a factor of 2 between the two. So the hash values, the hash length for the hash functions that people use are twice as long as the key length for symmetric encryption schemes, for example, AES. So typically today, the standard for AES still says 128 bits and hash functions 256 bits. Actually, today it's more recommended to use for AES bits keys of length 256 and hash values 512 accordingly. So what we want to do next is explain this factor of 2. And what we'll see is that, so we assume that for AES with, say, bit keys of length 256, the best known attacks on AES roughly have complexity 2 to the 256. So really the 2 to the key length. Okay? It's not quite true. They're a little bit better, maybe 2 to the 254 or 55, but really not significantly better. But as we will see, we have easily collision finding algorithms for hash functions with hash lengths 512 that only use time 2 to the 256. So it's the square root of 2 to the hash length that we need for the best, for the best known algorithms there. And if you want to have the same security level for the encryption schemes and for the hash functions, you'll see that we need to double, we have to have the factor of 2 between the two. Right? So that's why, that's the reason why we have in almost all recommendations you will see this factor of 2. And so we want to explain this attack. There are other attacks that have similar running time. This is the easiest one, which is based on the so-called birthday paradoxon, which is not a paradoxon, but a theorem. So here is a very simple algorithm to find collisions. It's not necessarily an efficient one, but it's one. Okay, so for simplicity, let us assume that we have a hash function whose hash length is n. Right? I don't want to introduce polynomials. You can easily extend that to other things. And then I define the adversary A as follows. So the key length is also n. Okay, so key length and hash length are the same. And so the adversary on input a key from 0, 1 to the n picks q of n for some value q many elements uniformly at random from 0, 1 to the 2 times n. So Q is some parameter. Don't necessarily think of it as a polynomial. It would be longer. For some number Q of n. And for all these values xi, it computes the hash value. And if there exists two indices ij with yi is not equal to yj, we output xi and xj. Okay. Otherwise, we output a failure symbol. Say. Okay. And we want to determine this number Q of n for which this algorithm with, say, constant probability finds a collision. Yeah? Yeah? So it just picks random arguments, checks whether there is a collision between two of them. And what we can show is the following. So I will mostly concentrate on the probability that there is two such things where yi is equal to yj. What we also have to consider, obviously, is that the corresponding x's are different. Right? Because otherwise this would not yield a collision. But with the same techniques, or actually, yeah, the same techniques basically that I use now, you can easily check that with high probability all these things are different, or with significant probability all of them are different. Yeah? And what we do, we simplify things a little bit. It turns out that it's not a simplification, but it's really very well justified. So let's look at the following situation. We pick y1 through yq for some number q elements uniformly at random from 0, 1 to the n. Then the probability that there exists ij, indices ij that are different, but where the yi's are equal to yj, that actually also applies obviously to our xi's, xj's, is at least q times q minus 1 divided by 2 to the n plus 2, and it's upper bounded by q times q minus 1 divided by 2 to the n plus 1. Okay. So you see there is only a difference of factor of 2 between the two things, right? Here it's plus 2, here it's plus 1. But the denominator is always the same. Okay. No. So we'll see how we can prove that. And then let's go to something else as well. We now look at the adversary in the generic attack game. And we assume that q now is a function such that for all n and n, this q times qn minus 1 is less than 2 to the n. Then what we can prove is that the probability that it finds a collision is at least q of n times q of n minus 1 divided by 2 to the n plus 2. Okay. Okay, and let me just check something that I don't do. Not doing it. Okay. Yeah, okay. Oops. Yeah. Okay. Good. Okay, and then, okay. So how do we get from this to this? Because this here assumes that the y's are chosen uniformly at random, right? But in our attack, things are not uniformly random, right? Because we use a hash function. Right? The y's correspond to the uniform random stuff. But what can show is that the probability for this algorithm is maximized if these things, the yi's, behave like independent uniform values. Okay? So this is justifying that, you know, we just apply this theorem here and then we get this here. Yeah? So being uniform, being uniform minimizes the probability of success. Sorry, it minimizes the success probability for this thing. So if things are evenly spread out, finding collisions is hardest. Okay. And we'll also in the exercises and tutorials, you will actually, for a simple case, you will justify that. And here's the justification. Let y be a random variable over some distribution D. And by collision denote the event had two independent random choices according to D yield the same element in Y. The identical elements. So you pick two elements, you sample according to the distribution D and check whether you find a collision. Yeah? And then this is the collision probability. The probability that your first choice is for overall y's, the first pick is a little y, and the second pick is also a little y. And that is overall y's this here. And you can easily show that this is minimized for the uniform distribution. Let's just do a simple example. Right? If you have uniform, so distribution D on, say, 0, 1. Yeah? And so the probability, say, y is 0, is that the first case probability of y is 1 is 1/2. Yeah? Then the collision probability, then the probability for collision is 1/2. You can either choose this formula, but also you can simply think about it. Pick the first element, you get any element, right? Doesn't matter. But conditioned on getting the first element, that the second element is the same, is 1/2. Right? Okay. Now, if you do the case where you have that it's more likely to pick 1. Yeah? Then the probability for collision here is 1/3 times 1/3. First one 0, second one is 0. The choices are independent, the picks, plus 2/3 times 2/3, which overall gives you 5/9, which is larger than 1/2. So finding collision here is harder. Right? So spreading out things evenly makes it harder to find a collision. if I told you this is my distribution, and you would have to guess which element I pick, guess one, because with 2/3 it's a better choice. Right? And here, well, toss a coin. Doesn't really matter. Right? So uniform is, for collisions, it's the worst distribution, the one that minimizes the collision probability. And for since with this algorithm we want to find collisions, so it's the thing that we need to analyze is if we want to get a lower bound, is the uniform distribution. And that's why we can go from here, where we assume this uniform distribution independent, to here, where the hash functions are not necessarily uniform. In fact, they are not. Okay? Okay. Yep. Good. Let's see what we get here. What does this mean? So assume that we want to have at least success probability 1/2. Well, how do you have to pick Q? Something around 2 to the n divided by 2, right? Well, if I say pick, let me do this. Here, if I pick Q to be, say, 2 to the n divided by 2 plus 1 plus 1. Okay? Let's see what I get. Well, is that good enough? 2 minus 1. Well, I should pick here, say, a 2. Yeah. Okay. So then Q of n times Q of n minus 1 divided by 2 to the n plus 2, that's certainly larger than, I just ignore the plus 1 in both cases. Well, here I subtracted, but they are not. I just do both of them, so that's 2 to the n divided plus 2 squared divided by 2 to the n plus 2. Which is 2 to the n plus 4. Just multiply the exponents, divided by 2 to the n plus 2. And that's already larger than 1. What? Yeah, so this is at least, no, that cannot be 2. Wait.
Is it a valid choice function? Because
No, it's not a valid choice. Yeah. So sorry, yeah. Thank you. This is not a valid choice. If I do too many things, this all breaks down. Okay. Okay, so I should do something here, let's say this here. This here. Does that work? That is still not correct. This here. If I pick just this here, okay? That's yeah, this works. Then I have that Q of n times Q of n minus 1 divided by 2 to the n plus 2 is 2 to the n divided by 2 times 2 to the n divided by 2 minus 1 divided by 2 to the n plus 2. This is 2 to the n minus 2 to the n divided by 2 divided by 2 to the n plus 2. And this is larger than 1/4. It's not larger than 1/4. It's larger than 1/8 for n large enough. Let's say n is larger than 16. I'm pretty sure that works. Yeah, that should work. Yeah. Yeah. Okay. So in that case, it works. Okay. Yeah. Okay. I need to include a condition here as well, I think. Okay. So let's do a little calculation to prove this theorem here, this lemma here. It's not too difficult. Okay. Yeah. So I need to include this condition here. I forgot that. I have to include this condition here as well. That this condition here for the Q, I have to include that here as well. Otherwise, things break down, as you will see. I forgot to modify that. Okay, and you'll see where I need that. Okay, so let's go to proof. We use the following facts. The first fact that we use is that it works for all x's. We have what we only needed for this guy here. We have that the other case is trivial. 1 minus x is less than e to the minus x. Very useful bound. Only useful when x is small. For large x's, so for x close to 1, it's not so interesting. The reason is, why is this here? Because this is 1 minus x plus x squared divided by 2 minus x plus x to the 4 divided by 4 factorial, and so on. Right? And this is an alternating sum. It converges absolutely. So when I go from here to here, I drop everything beyond that. And the first term that I drop is positive. And hence this becomes smaller. This is simple analysis. And we also have that in this range, we have that e to the minus x is less than 1 minus x divided by 2. This is a little bit harder to prove, but not much. Okay. Okay, so now I'm, yeah. Good. Okay. Yeah. So now let's continue. And first I want to prove the upper bound. Yeah? So the upper bound first. And so let collision is event that ij I not equal to j exist with yi is equal to yj. Yeah. And collision I comma j is the event yi is equal to yj. So that there is a collision at I comma j. I is not equal to j here as well. Now the probability for collision is upper bounded by the sum over all I is not equal to j, the probability collision I comma j. Right? It's a true upper bound, union bound. Right? Now the collision that the probability that we have a collision at I comma j is the probability that two elements picked uniformly at random from 2 to the n are identical. Huh? Yeah. Now, for each index I and j, this is the same. So how many indices pairs do we have? We have q times q minus 1 divided by too many indices pairs, index pairs. And the probability that two of these things are identical is 1 over 2 to the n. The first one you pick arbitrary, the second one that it's the same as the first one, then is 1 over 2 to the n. Right, so each individual probability is 1 over 2 to the n. And this then is what we wanted, right? That's easy. Okay. Good. Yeah. Because, okay, why did I divide by 2? Because I do not look at ordered pairs. Yi equals yj, so if I have a 2 and 5, and 5 and 2, is it?
You're just looking for existence.
Hmm?
If you're just looking for existence, you don't care about the order. You're just looking for sets of size 2.
Yeah, I'm just looking for sets of size 2. Exactly. I just look at two. I'm not looking at ordered things. Just two indices.
So then the sum is.
Yeah. Okay, sorry. You're right. So I'm. Is that better? I'm just looking. Yeah. I'm just looking at subsets of indices. Okay. They are really unordered. 2, 5, 5, 2. I don't care. Okay. So now we have to look at the the lower bound. Okay. And there I will use these things, both of them. So lower bound. So denote by collision K the event that the collision exists I, j less than K, such that yi is equal to yj. So among the first K elements, there's a collision. Yeah? And then collision as defined before is the same as collision Q. Right? And what I'm looking at is the converse of there's no collision. Okay, so let's see. So probability for collision is then minus 1 minus the probability for not collision Q. Okay. Yeah. Okay, so now let's look at this probability here. So the probability for not collision Q is the same as probability. Now I do the huge end collision K, K from 1 to Q. Not collision, sorry, yes, not. So, and now by conditional probabilities, you can rewrite this as follows. This is the probability for not collision 1 times, now comes the product, probability not collision I plus 1 given not collision I. I goes from 1 to Q minus 1. Oh, this is you condition on the first one, multiply with this thing. So let me just briefly tell you how you do that. So this here is probability of end not collision K condition on not collision 1 times probability of not collision 1. And then you continue here, pick out the next one, and so on. And you can always delete the rest. Yeah? And you can always, if there is no collision among the first 3 elements, there's also no collision under the first 2 elements. That's why you can ignore these ends. Yeah? Okay. So this guy here is 1. If you pick one element, there is no collision. No? Okay, so what is the collision? What's the probability of not collision I plus 1 conditioned not collision I? So I have no collision among the first I elements. But I do have, what's then the collision that I, also for the next element, I do have no collision? Well, if we set n to be, just to make life for us a little bit easier, capital N, this is among the n minus I elements that are the first I elements that I picked. They are all different. I need to pick one that's different from these elements. Well, so that's the probability, which is 1 minus I divided by n. That's why it's so useful to condition on this thing, because then I already know the previous ones are all different. And then the next one's also different. I'll just get this. So then we can replace this here. This is 1. This is product I from 1 to q minus 1, 1 minus I divided by capital N. Huh? And we want a lower bound on this. Hence, we want an upper bound on this. Yeah? We want a lower bound on probability for collision, so that's same as an upper bound on probability for not collision. Yeah? So, and then I can replace this here by the product e to the minus I divided by n. By my first thing which says that 1 minus x is less than e to the minus x. Yeah? Why am I doing that? Well, I'm doing that because products are annoying. And with this product, I replace that by a sum in the exponent. Sums we know how to deal with. Yeah? And so I'll just remove some of it here, but not all of it. So e to the and then product e to the minus I n I from 1 to q minus 1 is the same as e to the minus I divided by n I from 1 to q minus 1. Right? Which is the same as e to the minus q times q minus 1 divided by 2 capital N. Okay. Now I use my condition which I forgot. Namely, yes. So this is less than 1 minus q times q minus 1 divided by 4 times n, e to the minus x less than y minus x divided by 2. But I need for that x is less than 1/2. Which means that here that's only true q times q minus 1 is less than n. Then because if that's true, then I have this 2 here, and I'm less than 1/2. Yeah? Okay? And this is the probability this was the probability for non-collision. So then we know that the probability for collision is greater than 1 minus this here. But this here is 1 minus q times q minus 1 divided by 2 to the n plus 2. N was 2 to the n. And I'm done. Okay. So we recovered our condition here, which I forgot here, simply. But there it is. Yeah.
You also already used it for the conditional probabilities.
Yeah, these simply don't make sense.
Yeah.
If that would be larger. But here I only make sense if Q is, yeah. Anyway. So these two things, like this with the exponential, that's actually useful to know if you analyze probabilities, stuff like that. Both directions are very useful. And you will often see that in papers that people just use them. It's just standard stuff. Okay. And also, again, this conditioning thing, obviously, is a useful thing to do. Okay. So what did we see so far today? Or what did we see today? So we looked at hash functions. One thing to take away, like from a theoretical point of view, is we can replace in the hash then sign for one-time signatures, we can replace collision-resistant hash functions by universal one-way hash functions. And then we get our sequence really of constructions for secure digital signatures using just the existence of one-way functions as our assumption. But it's useful to keep this universal one-way hash function business in the back of your mind. It's often useful to do these things because they are easier to construct. And then you can, often you can plug them in. But we had to modify our hash and sign principle. We had to pick for each signature a new key for the hash function. That's because of the universal one-wayness that's weaker. Okay, and then we looked at the Merkle-Darmstadt construction to go from fixed length hash functions to arbitrary length hash functions. We saw again this chain-based construction and the tree-based construction that we also saw in the refreshing paradigm for digital signatures. And finally, today we looked at these at the birthday attack on hash functions, which explains why hash length are usually double the key length for symmetric encryption schemes in standardizations and in recommendations, like recommendations by the NIST, but also BSI, das Bundesamt für Sicherheit in der Informationstechnik. Okay, good. So that's it. All I wanted to say about hash functions. The last part of this course now will be about public key encryption schemes. We want to get rid of symmetric. We don't want to get rid of them. We want to make them usable, easier to use. And to do that, we look at methods that get rid of them, but then we say it's not best choice to get rid of them, but combine the two techniques to get something that's really good. So that is what we do starting next week when we start with public key encryption schemes. Just to give you a brief. Okay, but we'll do that next week. It doesn't matter. It doesn't really make sense to start with it today. But again, there we will see and look at what are the minimal assumptions that we need today to construct such things. But we'll also see very many practical constructions that are used all over the place. For example, we will look at hybrid encryptions. This is, again, most used in basically all usages of public key encryption schemes. You use it basically in this hybrid form. Okay, so that's it for today. Any questions? Otherwise, we'll meet again next week on Thursday morning. Okay, thank you.